In this video here, we're going to take a look at the equation of a plane in 3 dimensions. Now, following on from our previous video on the equation of a line in 3 dimensions, we now want to examine how we define the equation of a plane in 3 dimensions. Now, let's say that we have a plane that passes through a given point A, and it does this with position vector A. And now let R be an arbitrary point on the plane with position vector R. So that would look something like the following here. So we start from this fixed point O. We want to go to some arbitrary point on the plane here, which we denote as R. And it does this with position vector R here. Okay, so with position vector R. And we also have the position vector A here. Now, using this diagram then, we can easily see that by the triangle law, that the position vector R is equal to the position vector A plus this vector AR here. So what we're saying then is that if we want to go from O to R here, we can simply do that by using this position vector A plus this vector here, AR. Okay, so we'll include that with our diagram as well, like so. I've also got this second diagram here. So why is this second diagram relevant? Well, as we can see from this diagram here, right, the vector AR simply lies in the plane. So in that case, then, we can express the vector AR here in this form. So the vector AR is equal to lambda B plus mu C, where B and C represent non-parallel vectors in the plane, and lambda and mu are simply scalars. So in that case, then, the position vector R for the plane here can be denoted as follows. So R is equal to the position vector A plus lambda B plus mu C. So if we give this a breakdown here, this is what we obtain. So R here represents the position vector of a general point in the plane. A here represents the position vector of a point in the plane. B and C are non-parallel, non-zero vectors in the plane. And then finally here, lambda and mu are simply scalars. Now, I do appreciate that for one page here, that is quite a lot of information to take in. So what I'd say here then is do make a note of this equation here. So this is the position vector R, which we can denote as follows. And make a note here of what each letter represents. So R represents the position vector of a general point in the plane. A represents the position vector of a point in the plane. B and C are non-parallel, non-zero vectors in the plane. And then finally, lambda and mu are simply scalars. Okay. Now, before we take a look then at any examples here, we need to be aware of something called the normal vector. And you might sometimes hear this described as the normal to the plane. So the normal vector n here is a vector that is perpendicular to the plane. So what would this even look like? Well, let me try and sketch something here to help illustrate this concept. So if I sketch a plane here, like so, we'll get something that looks, say, like this. Okay, so this here is my plane. Now the normal vector then, as we've already noted here, n is a vector that is perpendicular to the plane. So let's say we've got this point here. So the normal vector then will come out of the plane like this here. And this is perpendicular then to the plane. So we'll get something that looks like this here. Okay. So for the normal vector then, well, we have the equation here of the normal vector. But before I denote that here, let's just carry on and then we'll come back to the equation. So a Cartesian equation of a plane in 3 dimensions can be written in this form here. So we have AX plus BY plus CZ is equal to D here. So A, B, C, and D are constants, and this vector then of A, B, and C is the normal vector to the plane. So going back to the equation here then, as we can see, the equation of the normal vector here is nice and straightforward. We simply use the coefficients then of x, y, and z as the normal vector to the plane then. So in this case here, we can denote this as AI, so AI plus BJ plus CK. Okay, just about enough room there. So there we have it. So that there is the equation of the normal vector to the plane. And as I've already mentioned, just use the coefficients here of a Cartesian equation of a plane in 3 dimensions like this here. Okay, so ABC, that is our normal vector. And then finally here, you can derive this result using something that we call the scalar product. So you haven't seen the scalar product yet, We're going to introduce that as part of the next video here. So obviously don't worry about that just yet here, but just be aware that it is something that you can derive using the scalar product. Okay, so we'll learn a little bit more about that within the next video. So there we have it. That gives us everything that we need here then for our introduction to the equation of a plane in 3 dimensions. All we're going to do now is take a look at 2 practice questions here for the equation of a plane in 3 dimensions. So let's get started here then with question 1. So what do we have here for question 1? Well, what we've been given is a Cartesian equation of the plane pi, which is given as 2x plus 3y minus z is equal to 8. Now for part A then, it just asks us to verify that the plane passes through this given point here of -2, 5, and 3. Now, if the plane passes through this given point here then, if we substitute this given point here into the left-hand side of this equation for the plane pi, then what we should obtain is the right-hand side here of 8. So let's just do that then for part A. So for part A then, we get 2 lots of x here, so 2 lots of -2. 2 lots of -2. We then get 3 lots of y here, so 3 lots of 5. 3 lots of 5 there. And then finally minus z, where z is equal to 3. So -3 there. So now let's simplify this here and see what we get. So 2 lots of -2, we get -4. 3 lots of 5, we get 15. And then -3. Okay. Well, clearly then 15 minus 7 here, we get a as required. We get a as required there. What that shows then is the plane passes through this given point here. So therefore, plane passes through -2, 5, and 3 there. Okay. So there we have it. Nice and easy. That gives us the solution to part A. Now for part B then, it says write down an equation of the normal vector to the plane. So n here, this would be the equation here of the normal vector to the plane. This is nice and straightforward, right? So to obtain the equation here of the normal vector to the plane, we simply use the coefficients here of x, y, and z. So in that case then, what we get here is 2i. We then get 3j here, so plus 3j. And then finally here, we get minus k. Okay, so just notice then, is 2, 3, and -1 match up with the coefficients here of the left-hand side. Okay, so there we have it, nice and straightforward. That gives us the solution there to question 1. So to finish with here then, let's just take a look at one more question. So we have question 2 here, and for question 2, we're told that a Cartesian form of the equation of a plane is given as 2x plus 5y plus z is equal to 10. It then asks us to find a vector form of the equation of the plane. So to get us started here then, what we need is 3 points that lie in this plane here. Okay, and the 3 points that you choose might be completely different to mine. That's fine, as long as the 3 points you choose do lie within this plane here. Okay, so the 3 points that I've chosen here then are as follows. So I've got the point A, and the point A then has coordinates of 5, 0, 0. I've got the point B here with coordinates of 1, 0, 8. And then I've got the point C here to finish with. This is my last point. And the point C then has coordinates of 0, 1, and 5. Okay. Now, to continue here, what I'd recommend doing is a diagram. I think it helps to illustrate the problem here that we have at hand. So we start from a fixed point here. Let's call this O. Okay. So this is my fixed point here, O. And we also have our plane here. So if we draw our plane, we'll get something that looks like this here. Okay. By the way, this sketch doesn't have to be perfect. Just as long as you can kind of illustrate and visualize the problem at hand, I do think it's very helpful. So this is my plane here. And we want to go from this point here, O, to some point on the plane. Let's call this R here. Okay. So we want to go from O to R. Like so. And we can call this here then. So from O to R, we can denote this here as the position vector R. Okay, so R like that. Now we've also got these 3 points here that lie on this plane here. So I've got the point A, the point B, and the point C. And these 3 points then lie on this plane. So let's say that this here is the point A. This here then is the point B. And this here then is the point C. Okay. So we want to go from O to R, but to get us started, we're going to go from O to A. Okay, so A is just some point on the plane, right? Which in our case is 500, but generally speaking, this is just a general point on the plane. So we go from O to A here. Okay, like so. And again, we can denote this here as the position vector then, and in this case, this would be the position vector A. Okay. We've then got these 3 points here that lie on the plane. So we can now go from A to B or from A to C here. We go from A to B, or we could denote that here as the vector then, AB. Okay. And then in a similar fashion here, we can go from A to C. That should be a straight line, but you get the idea. We can go from A to C. And again, we can denote this here as a vector. So this is the vector AC here. Okay. Now, if we just think about the equation of a plane here, then we know that R is equal to the position vector A here plus lambda B. So lambda B here plus mu C. Okay. So B and C here are just some non-parallel vectors within the plane, and lambda and mu are just simply scalars. Okay. Now, to help illustrate further this concept, what I'm going to do here is a second, basically like a mini diagram here, just to demonstrate this concept then of these two vectors here, B and C. So think back to, we introduced this here at the beginning of this video. Let's say this is our plane here, and we've got these two vectors, right? These are my non-parallel vectors. Okay. And we'll call this vector here B, and we'll call this vector here C. Okay. I should have my little lines underneath. There we go. Like so. Okay. So in that case then, altogether here, if we think about this here then, so we've described this as B, right? But in that case, we could just describe this as the vector AB here. Okay. We can replace B here with this vector AB. And again, in a similar fashion, we can replace C here with this vector AC. Okay. So in that case then, R is equal to the position vector A plus lambda times by this vector AB here. Don't forget lambda is just simply a scalar. And then same again here with mu. So we get mu times the vector AC here. Okay. So now what we need then is these two vectors here, the vector AB and the vector AC then. So for the vector AB here, nice and straightforward, this is simply B minus A. So what do we get then? I'm going to get 1 minus 5, so that gives me minus 4. You then get 0 minus 0, so that's just 0. And then finally 8 minus 0 gives us 8 there. Okay, we get minus 4, 0, 8. That's the vector AB. Doing the same here then for the vector AC. This will just be simply C minus A then. We get 0 minus 5, so we get minus 5 there. We then do 1 minus 0, so we just get 1. And then finally here, 5 minus 0 just gives us 5 there. Okay. That's the vector AB. That's the vector AC. The only thing that we don't have here then is the position vector A here. But the position vector A then, so the position vector A here is simply the vector OA here. Okay. Which in this case then is going to be 5 minus 0, which is 5, 0 minus 0, which is 0, and then again 0 minus 0, giving us 0 here. So the vector OA then is simply 5, 0, 0. Okay. So now we have everything that we need here then to find a vector form of the equation of the plane. So altogether then, what we've got here is the following. So r is equal to the position vector A, which is the same as the vector OA, which is 5, 0, 0. We get 5, 0, 0 plus lambda times the vector AB here. We get lambda times minus 4, 0, 8. So lambda minus 4, 0, 8. And then we get mu times the vector AC here. So mu times this vector here, AC. What we get then is minus 5, 1, and 5 there. Okay. And there we have it. So this here then, this here gives us the solution to this problem here, this final question, question 2. Now, just note here that your solution, what you get, is dependent on the 3 points that you choose, right? If you chose 3 completely different points to what I had here, then your solution will look completely different as well. If you chose the same 3 points as me, then you should get something like this here, okay? But again, this is dependent on the 3 points that you choose, at the beginning of the question. So if you've chose 3 completely different points to what I had here, just make sure that your answer here matches up in a similar kind of fashion, right? So there we have it. This is our solution here. So that's the solution to the very last question here, question 2. And that brings us to the end then of this video here on the equation of a plane in 3 dimensions.